A crane can lift hundreds of tons into the sky, but the most terrifying moment is not when it moves. It is the moment when everything depends on a few invisible systems working perfectly. Imagine a machine taller than a skyscraper, carrying a load heavier than a passenger airplane, while sensors, computers, and engineers fight against gravity every single second. But here's what nobody tells you. The real power of a crane is not only in its steel and motors. It is hidden inside the safety technology that prevents one small mistake from becoming a disaster. Every movement of a crane creates invisible forces. Wind pushes against the boom, cables stretch under extreme tension, and thousands of metal parts experience stress that human eyes cannot see. Think about this. One safety sensor can detect a dangerous condition before the operator even notices a problem. And this is where it gets truly extraordinary, because modern cranes are no longer just machines. They are intelligent systems designed to think, react, and protect human lives. Today, we are going inside the hidden world of crane safety systems. We will discover how raw materials become precision-engineered protection devices, how factories build the sensors and controls that guard enormous lifting machines, and how engineers test these systems until failure is almost impossible. But before a crane can protect the world above ground, its journey begins deep underground with the materials that create its strength. Before a crane safety system can monitor a 500-ton lift, it starts with materials that come from every corner of the planet. High-strength steel often begins as iron ore extracted from mines in countries like Australia and Brazil, where giant machines remove millions of tons of rock every year. The ore is processed, refined, and transformed into steel with carefully controlled chemical compositions. Most people never think about this, but a tiny sensor and a massive crane frame share the same beginning, the Earth itself. The steel used in crane structures must survive extreme forces, with some grades reaching tensile strengths above 700 megapascals. After mining, the material travels thousands of kilometers by rail and ship before reaching steel mills where temperatures rise above 1,500 degrees Celsius, or 2,732 degrees Fahrenheit, turning raw rock into liquid metal. The sound is overwhelming, roaring furnaces, sparks flying, and massive machines moving with perfect timing. But steel alone is not enough. The real secret is the precision hidden inside the safety components. Crane safety systems require more than steel. They depend on copper for electrical wiring, rare metals for electronic components, silicon for sensors, and specialized alloys for precision parts. Copper may travel from mines in Chile or Peru, where massive operations extract millions of tons annually, then move through refineries before becoming the tiny pathways that carry information through a crane's brain. A single crane may contain kilometers of wiring connecting hundreds of sensors. But here's the surprising part. The smallest parts often carry the biggest responsibility. A load moment indicator, a wind sensor, or a pressure sensor may weigh only a few kilograms, yet it controls decisions involving hundreds of tons of moving weight. These components must be manufactured with microscopic accuracy, often within fractions of a millimeter. A tiny error inside a sensor could create a dangerous chain reaction, which is why the journey from raw material to finished safety system is controlled at every stage. The environmental cost of these materials is another hidden story. Mining, transportation, and metal processing require enormous energy, and factories constantly search for cleaner methods through recycling and improved efficiency. Modern crane manufacturers increasingly reuse steel, recover metals, and design longer-lasting components to reduce waste. But after these materials arrive at the factory, the real transformation begins, where raw elements become a safety system capable of controlling giants. And now the journey reaches the most important stage. Inside the factory, steel, electronics, and software must come together into one perfectly synchronized system. But how do engineers build technology that can stop a crane carrying hundreds of tons before danger happens? The answer lies in a manufacturing process where every second, temperature, and measurement matters. Inside the factory, the first step begins with cutting and shaping the structural components that will protect the crane during operation. Massive steel plates arrive weighing several tons, and CNC cutting machines slice them with laser precision using temperatures that can exceed 3,000 degrees Celsius or 5,432 degrees Fahrenheit at the cutting point. The machines move at speeds measured in meters per minute, creating perfectly shaped parts while sparks fly and the smell of hot metal fills the air. But this is only the beginning, because every safety system must eventually become accurate enough to predict danger before it happens. After cutting, the steel components move into machining areas where giant CNC mills remove material with incredible accuracy. These machines rotate cutting tools at thousands of RPM while maintaining tolerances measured in microns. A worker watches through protective glass as the machine removes tiny layers of metal, producing the exact dimensions needed for mounting brackets, sensor housings, and safety mechanisms. What happens next surprised even experienced engineers, because the smallest adjustments can decide whether a crane performs safely for decades. The next stage is welding, where individual pieces become a single powerful structure. Robotic welding arms create intense electric arcs reaching temperatures above 6,000 degrees Celsius, or 10,832 degrees Fahrenheit, melting metal surfaces together in seconds. The factory becomes a world of blue-white flashes, sparks, and controlled heat as engineers inspect every weld for strength. But here's what nobody tells you. A weld that looks perfect from the outside can still hide a weakness inside. To discover hidden problems, manufacturers use advanced inspection methods like ultrasonic testing and X-ray scanning. Sound waves travel through metal at precise speeds, detecting cracks smaller than the human eye can see. Some inspections happen under controlled pressure tests where components experience forces far beyond normal operation, sometimes exceeding 125% of their rated capacity. The goal is simple: find the weakness inside the factory, not thousands of meters above the ground. Now the electronic brain of the crane safety system begins to take shape. Circuit boards are assembled in controlled environments where robotic machines place microscopic components at incredible speed, sometimes thousands of parts per hour. The sensors are calibrated using exact pressure, weight, and movement simulations to ensure they report accurate information. A sensor measuring cable tension, for example, must recognize tiny changes before a dangerous overload occurs. The heart of the system is the load monitoring technology. Imagine a crane lifting a huge steel beam while invisible forces constantly change with every movement. Sensors measure load weight, boom angle, cable tension, and wind speed in real time, sending thousands of signals every second to the control computer. If the system detects danger, it can warn the operator, automatically prevent unsafe movements. This is where a crane stops being a machine and becomes a guardian. But safety does not end with electronics. Hydraulic systems, brakes, motors, and emergency controls must all work together perfectly. Hydraulic pressure inside crane systems can reach hundreds of bar, creating enormous force through compact machinery. Engineers run continuous cycles where cranes lift, lower, stop, and restart thousands of times to simulate years of real-world operation. The machines shake, the motors roar, and every vibration tells engineers a story. Before leaving the factory, every crane safety system faces one final challenge: proving it can survive the unexpected. Engineers recreate harsh conditions including strong winds, sudden stops, overload situations, and emergency failures. The system must react instantly, because in the real world there is no second chance. But the most advanced testing technology still leads to one question: can machines truly guarantee safety, or does human skill remain the final line of defense? Modern crane safety systems have entered an age where machines can almost see, think, and predict. Inside advanced factories, artificial intelligence, laser measurement tools, and smart sensors work together to create a digital nervous system for massive lifting machines. Imagine a crane operator moving a load hundreds of feet above the ground while a computer watches every angle, every vibration, and every change in the environment. But here's what nobody tells you: the most powerful safety feature is often the information nobody can see. Laser scanners now inspect crane components with incredible accuracy, creating digital maps that reveal even tiny surface changes. These systems can detect wear, deformation, or alignment problems measured in fractions of a millimeter before they become serious failures. A robotic scanner moves around massive steel structures, sending millions of measurements back to engineers in seconds. The result is a level of precision that human eyes could never achieve alone. Inside electronics testing rooms, AI vision systems examine thousands of tiny details on circuit boards and sensors. High-resolution cameras capture defects invisible to workers, checking solder joints, wiring connections, and component placement. Some systems can analyze hundreds of parts every minute and instantly reject anything outside strict specifications. What happens next surprised even experienced engineers, because sometimes artificial intelligence finds problems that humans never noticed. Every safety system must pass international standards before it reaches a real construction site, port, or industrial facility. Engineers test emergency stop functions, overload protection, sensor accuracy, and communication systems under extreme conditions. Components are checked against strict engineering requirements, with measurements often controlled within millimeter or even micron-level tolerances. A single rejected part may look perfect to a person, but machines know the difference. The toughest test comes when engineers try to break the system. Full-scale cranes are pushed through simulated storms, overload conditions, and emergency scenarios. Wind sensors are tested against powerful air systems, load monitoring devices face extreme weights, and control systems are forced to respond under pressure. The goal is not to prove the crane works perfectly. The goal is to discover how it reacts when everything goes wrong. But even with the most advanced robots and computers, one human skill still remains impossible to replace: experience. A veteran crane engineer can hear a strange vibration, notice a small movement, or recognize a problem before a sensor creates an alarm. Years of working around these machines create a sixth sense built from thousands of observations. Technology protects people, but human judgment completes the system. The final stage is reliability testing, where manufacturers simulate years of operation before a safety system ever reaches customers. Machines repeatedly lift, stop, move, and restart thousands of times while computers record every reaction. Some systems are designed to operate for decades in rain, heat, dust, and freezing temperatures. And this is where the next mystery begins. How did these incredible safety systems transform from simple mechanical warnings into the intelligent technology we trust today? The world of crane safety systems is much larger than most people imagine. Every year, thousands of cranes are manufactured, upgraded, and equipped with advanced monitoring technology across construction sites, ports, factories, and energy projects. The global crane industry is worth tens of billions of dollars, and safety technology has become one of the fastest-growing parts of this market. Think about this: behind almost every skyscraper, bridge, shipyard, and industrial project, there is a hidden network of sensors working silently above us. Today, the biggest crane manufacturing and engineering centers are spread across countries like China, Germany, Japan, the United States, and Finland. China produces a significant share of the world's cranes due to its enormous construction industry, while European manufacturers are known for advanced engineering and precision systems. Japan and Germany have pushed automation and safety technology forward, creating machines that combine mechanical power with digital intelligence. The competition is no longer only about lifting heavier loads, it is about making every movement safer. Over the last 50 years, crane safety has changed dramatically. Older cranes depended heavily on operator experience and mechanical warning systems, but modern machines use computers, GPS positioning, artificial intelligence, and real-time monitoring. In the past, a warning might come after a problem started. Today, systems can predict risks before they happen. Most people never think about this. The safest crane operation often begins before the crane even moves. The number of workers connected to the global lifting industry reaches millions when you include crane operators, engineers, maintenance teams, and construction workers. Every improvement in safety technology protects not only machines but human lives. Modern systems reduce risks from overloads, unstable conditions, electrical failures, and human error. But here's the surprising part. The greatest achievement of crane safety technology is not that it makes cranes stronger. It makes dangerous situations easier to avoid. Did you know? Some modern cranes can monitor their own condition by analyzing vibration patterns, temperature changes, and operating history. Did you know? A small sensor costing only a fraction of the crane's total value can protect equipment worth millions of dollars. And did you know? The future of cranes may include fully autonomous lifting systems where artificial intelligence manages entire operations with minimal human control. Over the next decade, Crane safety is expected to become even smarter. More machines will use connected sensors, cloud-based monitoring, digital twins, and predictive maintenance systems that identify problems before failures occur. Instead of waiting for a component to break, engineers will replace parts based on real-time data. The future crane will not simply lift, it will understand, communicate, and make decisions. But behind all the numbers, technology, and engineering achievements, one truth remains. A crane is still a machine fighting against gravity, weather, and extreme forces. The reason these giants continue working safely is because thousands of decisions, materials, tests, and human skills come together perfectly. And now we return to where this journey began, the hidden systems that make impossible lifting operations feel almost effortless. From the deepest mines where raw materials begin their journey, to the factories where steel and electronics become intelligent machines, crane safety systems represent one of the greatest examples of human engineering. Every sensor, every cable, every circuit, and every line of code exists for one purpose: keeping enormous forces under control. Think about this the next time you see a crane rising above a city. Behind that massive structure is a hidden world of precision, testing, and technology working together every second. Most people only see the crane moving a load through the sky. They never see the thousands of hours of engineering behind that movement. They never hear the factory machines cutting steel, the welding sparks creating strength, or the computers analyzing every vibration before danger appears. But this is where it gets truly extraordinary. The safest machines are built not by one invention, but by millions of tiny details working perfectly together. The future of lifting is already changing. Artificial intelligence, automation, and predictive systems are creating cranes that can understand their own condition and prevent problems before they happen. But behind every smart machine, there will always be human creativity, engineering knowledge, and the desire to build something safer than before. The next generation of cranes will not just move the world forward, they will protect the people who build it. So the next time you watch a crane lift a massive structure hundreds of feet into the air, remember there is an invisible guardian working behind the scenes. A network of sensors, machines, engineers, and technology standing between power and danger. What looks like a simple movement is actually a masterpiece of planning, science, and precision. The world sees the crane. But now you know the story behind the safety that makes it possible. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.